Yeah. So to everyone, let me introduce Vishal. Vishal and me were there in ISC, and it was first that like we got interacted. And Vishal, as I already sent bio to all of you in Telegram group and over to mail also. So Vishal had joined ISC in 2017, and like we were together in ISC. He was AIR 7 at his time, which means 2017, and most of his MTech research was in machine learning. And he was in ISC, he was a very diversified person, which means like he has taken courses related to machine learning. He has taken courses related to operating systems. He has taken courses related to maybe compilers. So he has taken all sort of courses which range from different pools like pool A, pool B, pool C. And yes, so he was like one of the top ranker in our batch, and most of our students, like most of our batchmates, used to go to him for any problem that we used to face, either in machine learning or in systems or in algorithms or be it any subject. So Vishal was one person to we go for. And currently Vishal is in IIT Delhi. He is pursuing his PhD under Professor Mosam. So Mosam is his main guide, and I'm not sure if he's like interacting with other professors. Maybe Vishal can tell you about more. And also like he was with me with at Amazon. So at Amazon he has worked around 2 years as an applied scientist. So we were together. Like I was there for one and couple of months, 1 year and I think 2 months, and Vishal was there for almost 2 years. So at Amazon also our tenure has overlapped, and obviously at ISC. So yeah, over to you, Vishal. Like thanks for joining in. And like yeah, so before I say anything, maybe you can introduce yourself and maybe you can proceed. Yes.
Uh, I hope I am audible.
Yes, you are.
Yeah. Hey, hello everyone. I'm Vishal. So I will be teaching operating system. So currently I'm working in machine learning and chatbots and all. And like, yeah, still I will be teaching operating system because since my BTech times, it is one of my favorite subjects. And so even in IIC, like Sachin mentioned, right? Like I took operating system courses and all that. So because I like it through and through, and like some time back I was also working in industry there. My job was also based on operating system. So I am basically fan of this subject, and that is why I am very happy to teach this as part of Go classes. So nothing more. So I'll get to the lecture soon. So in initial two lectures, I think it's very important that you understand the basics of operating systems even before we go into any of this interesting topics like process management, memory management, and all that. Before even going to that, I think we have to go through some basic stuff, and that should help you actually to understand what are these different components are doing in an operating system, and what are exactly the problems that they are trying to solve, and like how exactly are they are trying to solve. So today's lecture and some part of the tomorrow's lecture also, I'll be covering most basic stuff. I'm pretty sure some of this has already been covered by Sachin and Deepak in other courses, for example, in this like C and like this discrete mathematics and whatnot, right? So the point being that is even though this concept seems very easy, it is very crucial that you all understand that, and you always keep those things in on back of your mind when you actually uh, start learning about operating systems, right? So just let me adjust my screen and we'll get started. Can somebody confirm that they can see my slide? Okay, nice. So let's get started. Keep the chart open also. Okay, so this is like the syllabus that you have for GATE 2023. I basically copy pasted it from the official browser that they have released. So it doesn't look that much, right? Like only 5 topics on top of it. So some system called processes, threads. So basically process management. And then you have this deadlock and all, which is somewhat part of the process management itself. But yeah, it's a little bit broader topic than that. Then you have this CPU and IO scheduling and memory management and file system. So this is just something that I have directly copy pasted from the Gate browser. So we won't be covering all these things in the order that have been mentioned here. So we'll try to follow some systematic order rather than just going with this order. It overlaps with this particular thing, but yeah, we'll try to do our best and follow some logical sequence. Okay. So yeah, so this is like some image that I got from Wikipedia, and this is basically what we will try to understand throughout this particular topic, right? What exactly is operating system? So if you see here, so operating system is all about helping the user. If the user will be using a particular hardware or a particular system, right? So operating system is all about helping user achieve some task. So for example, the task can be add 2 numbers. Right, it can be add 2 numbers, it can be play a song, it can be watch a video, it can be open Firefox or whatnot, right? So user wants to achieve these particular tasks. So for this particular task, then there will be some application program. So application program is basically what you have is like a calculator, right? So you see this numbers and all that, then there is a plus sign, there is a minus sign, there is a multiplication, whatnot, right? So you basically use that application to achieve this addition of 2 numbers. Now this calculator itself has to run on this hardware, right? So this hardware is basically your CPU, that's Intel CPU or like AMD CPU, i5, i7, whatnot, right? It has this some RAM, right? Whenever we buy a computer, we see there is some CPU, there is some RAM, and there is some other components, right? Like whatever, right? So the calculator has to use this hardware to achieve this task, that you tell calculator to add 2 numbers and it will go to hardware and it will do something with it and it will perform the addition for you, right? So now for calculator to basically use this hardware in a very effective manner, it requires to do certain things, right? And what those certain things are is basically what operating system does for it. So it's mostly what we call it as resource management. So ideally calculator should have done this, but this is something that most of the application program need, right? So for example, what RAM we should, what portion of the RAM it should be using, how the CPU it should, if there are multiple CPU, which CPU it should be using, and there are many other things that we came to know as we move forward throughout this particular topic, right? So this resource management is something that calculator needs to use this hardware in a proper manner. Again, I am telling something which is out of the blue. Like, so what do you mean by proper manner, right? So what do you mean by proper manner? That we don't know. So we'll define these things as we move along. But yeah, there is there is a particular way in which the application should use the hardware, right? So for example, it should not happen that calculator is using all the CPUs, right? If calculator is using all the CPUs, then your browser will not work, which was running in background. Or maybe you are running a song in background, and if you run the calculator, it's using all the CPU, your song will stop playing, right? So there is a proper way. Again, the proper changes, the meaning of proper we will define more concretely as we move forward. But this it has to access the hardware in a proper manner, right? And for that it requires resource management. And this is not a very specific to the calculator actually, but it is common for most of the application programs. And to perform this resource management, they have written a very specific type of code which is known as operating system. Okay, so this is again only one of the duties of the operating system, but it is one of the major one, right? So user just only cares about adding 2 numbers and it uses calculator. So for user, everything is very easy because it just sees for user, it sees the screen, there are numbers, it presses the buttons and all that, right? While for application, it's a little bit harder because it again, you have to allocate memory and use CPU and whatnot, right? For operating system, it has to enforce that there is a proper way in which these resources are used by calculator, and hardware is basically the workhorse, right? It will do all the tasks. Again, it is a very, what you can say, it's kind of dumb because it only knows you have to tell it everything. You have to tell hardware everything. So we'll get to this also. So it is a very, very, very dumb machine. You have to tell it how to do things in a very, very minute manner, right? So for example, even if you say add two numbers, you have to tell is what is the first number, what is the second number, where is it stored, how to read that number, how to do addition. All those things you have to like stepwise, you have to mention it to the hardware. And all those tasks basically operating system will do for you. Will again, I am telling it in a like a hand wavy manner, but these things at this point will be abstract only. So even if you go through books and all, they will tell you these examples, whatever I am telling you, and like again, it will make sense. But to understand it in from a deeper level, you need to understand operating system at a much like fine grained levels. So we'll get to that along the topic, right? So any doubt in this? Okay. Okay. So now the basically the what we want to do in this particular course is like understand what this guy is doing, right? So we know it's doing resource management. We are saying it at a very high level, but like what exactly it is doing is what we want to learn, right? So now if you see, this operating system is very closely connecting to the hardware, right? So because it has to manage the hardware, right? So operating system and hardware is kind of like married to one another, and like so if you want to write an operating system or if you want to understand an operating system, it is essential that you understand the hardware properly. Unless and until you understand the hardware properly, you won't be able to understand the operating system. Okay. So because it is the program which works directly with the hardware, no other application program will work directly with the hardware. Only the operating system works directly with the hardware. So before even we go to operating system, we should understand what kind of hardware for which the operating system is being written or it's working with. That is the first part, right? Again, once we move forward, we'll see that there are some problems within the operating system itself. So for example, again, I am giving some future reference. If you don't understand this terminology, I specifically started with this calculator. At the end of this class, I will show you how painful it is to run a calculator on hardware directly. So just hang in there for a bit. I'll tell you why it is very difficult for calculator to run directly on hardware, right? So it can run, but there are so many issues that it has to take care of before you forget about writing the calculator code. All other things will come into picture, and we'll find that okay, this is something I don't want to do. So at the end of the class, I have that example, and I will explain that to you at that time. Okay. So what I was saying is that like we will understand the hardware first, but in the future, when we start looking into this more detailed topics like process management or memory management, you will find that there are some things for which the operating system itself requires some help from the hardware. So it's not like the hardware is developed independently of the operating system. So hardware itself has some components that makes the job of operating system easier, right? So again, at this point, I will not go into details for this, but as you go forward, even in starting from this process management itself, you will get to know what are these components that are there in hardware, which are required by the operating system to function properly. Okay. So again, like these concepts, many of you might already know, but again, I'm doing it from this very, very low level because even though they look very simple, they have kind of like they recur as we move along this topic. So for example, binary numbers, we know binary numbers from things like 9th or 10th standard or something like that. But binary numbers, you will again come into memory management when you have this address spaces and all, right? So it's always better to keep this basics in mind. Again, these are the topics. For example, these topics, right? These topics will be covered in this computer organization. Again, there it will be covered in much more detail. So we will be here in this lecture and maybe some part of the tomorrow's lecture. We will try to cover it in a operating system point of view. So we won't go into too much details, but we'll basically try to cover only those points which are required by the operating system. So yeah, exactly, right? So binary numbers you already have covered in digital logic and whatnot, right? So this is just a refresher on this, so that like some of the computations or problems that we see later in the class, you should be able to basically connect that back to your digital logic thing, right? So by the way, all these systems are developed through digital logic only, so it makes sense to have a refresher on that, right? So again, this is computer organization. This will be covered in detail there. Then you have this fetch, decode, execute. Again, this is somewhat part of the computer organization, but we will again study it in operating system because we want to understand what interrupts are. So unless you understand fetch, decode, execute, you won't understand interrupts. So yeah, so that's why interrupt comes in the last. So these are the basic topics that I'll try to cover in today's class, and I will discuss this. If you have some doubts and all those things, we'll discuss at the end of the class, right? So let's get started. Yeah, so like again, these topics will be covered in multiple areas, right? So microprocessor also, it might be there in computer organization, it's definitely there and all, right? So if you have any doubt in any of these concepts during the class, you just ask the question, okay? So again, right, like binary numbers are basically zeros and ones, right? So every number that you have in decimal, we can represent using some kind of a binary bits or binary digits, right? So for example, this 10 in decimal, you can represent it something like this, 1011, and 15 is basically represented as like 1111, right? So again, each of this digits here, we call it a bit. So basically this 15 is a 4-bit number, right? And again, this is a 4-bit number. So if you have 16, 10, it's basically written as this in binary, right? And it is again like a 5-bit number, and so on and so forth, right? So in actual hardware, when you go into the hardware, these 1 zeros are actually voltage levels, right? So again, these are the details that you don't need to indulge too much into, but it's basically some voltage level, like 1 is basically +5 and 0 is 0 or something like that. That is the hardware implementation, right? So again, like depends on the hardware, but this is generally the case. You have 2 levels. 1 is basically +5 and 0 is basically 0, right? So I guess like this binary, again, like +5 -5, we don't care, but there is some, what I want to say is like all these things are there in hardware in some form, right? So at this point, we are only concerned about hardware, right? So like these are like some basic questions that you have. So in your hardware, let's say you have n bits, like for example, something like this, 0, 1, 2, n minus 2, n minus 1. These are the n bits that are there in hardware. Okay. So what we want to understand is like, if my hardware has this n bits, how many numbers can it represent? Okay. Is the question understood by everyone? If anybody has any doubt, they can ask. Okay. So basically, you have this n bits in your hardware, and we want to ask how many binary numbers we can represent using this n bits. So again, like it's basically combination, right? So every bit can have 2 values, zeros and one. So here you can have 2 values. Here again you can have 2 values. Here again you can have 2 values, and so on so forth. Again 2 values, again 2 values, right? So the total numbers that you can represent is basically multiplication of this. So this is basically per combination formula that we have, right? It's basically, then you get is basic 2 raised to n, because there are n positions, right? So total numbers that you can represent with n bits is 2 raised to n. So the lowest number, so now I am saying unsigned integers only, okay? And in this lecture, we only consider unsigned integers, okay? So we don't have to worry about signed integers throughout operating system. If we do, I'll let you know. Apart from that, it's mostly unsigned integers as far as operating system is concerned. Okay. So the lowest number that you can represent using n bits is basically 0 when you keep all zeros and all, right? And the highest number is basically this one, 2 raised to n minus 1. So these are total 2 raised to n numbers. Okay. I hope this is understood. Any doubt up to this point? No, right? Okay, great. So another question, again, these topics might seem to be kind of like trivial, but this will come in handy when we go into memory management, especially when we are solving problems, right? So again, now I have an integer n. So question is, what are the minimum number of bits that are required to represent this number n in binary? Okay, so for example, I have, let's say, number 17. So how many bits do I need to represent 17 in binary, right? So for me, I know that 17 is basically this. So I would say 5 bits, right? So again, we can have something like 22. Again, it will have around 5 bits only, right? Then if you get 30 up to 31, it will be 5 bits. And 32, it will be 6 bits. And so on and so forth, right? So for this, you basically have a formula, which is basically something like this, right? Number of bits required will be ceil of log of. So okay. Yeah, it will be basically ceil, not this one. It will be ceil of log of 2n, right? Not plus 1. Sorry. Okay. So this is the formula that we get for getting the number of bits required for representing some number n. But there is a catch here. So for example, what if the number n is a power of 2, right? So for example, if I want to represent 2 raised to 4, which is basically 16, right? Right. So what we basically get here is 4, right? But we know for 16 we require 5 bits, right? Yeah. So I'll explain ceil now. Okay, I'll do that. Okay. So ceil function is basically for any number, let's say any number x, right? Ceil of x is basically the or may not the largest. It's basically the smallest integer which is greater than or equal to x. So we consider smallest integer which is greater than some number x, right? So for example, it's 1.5. Then the smallest integer which is greater than 1.5 is 2. So ceil of 1.5 is basically 2. Okay. Similarly, if you have 1.8, it will again be 2. If you have 2.9, it will be 3. Something like this, right? That is what we call as a ceil function. Again, it can be represented as this also. This is just a symbol for ceil function. Again, the smallest integer which is greater than this number x, right? There is floor function also, which is the largest integer less than x. So if, for example, if you consider floor of x, it will be again the largest integer which is less than x, right? So for example, for 1.5, the floor will be 1, right? Right, less than equal to x. Again, for 1.8, floor will be 1. For 2.9, floor will be 2. Is everybody clear about ceil and floor functions? Okay. So coming back to this particular problem, so what we want to find is what is the minimum number of bits which are required to represent a particular number n, right? So so the formula that we get is basically this one: b is equal to C log of 2n. So what we take the number n, we take the log of that number with base 2, and then we take a seal of that. So for example, if I take 15, right? So log so 15 is basically what we know that it is less than 2 raised to 4 because it's less than 16, and it is greater than what 2 raised to 3, which is basically what 8, right? So this is something we know, right? And if you take a log of this 15, it will be somewhere between 3 and 4, right? Something like that. So log of 15 with respect to base 2 will be between 3 and 4, right? And if I take a seal of that, then it will be 4, right? Is that understood? So I'll write it down here again. Log of 15 will be some 3 point something something something, some number here. And if I take a seal of that, 3 dot something 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 something, it will be basically 4. So I will take 4 bits, right? So that is the formula. But this formula will not work if you have if your n is in power of when n is in power of 2, right? So for example, if your n is 16, which is 2 raised to 4, and if you take this formula, right? So what you will get is basically this. So again, I'll write it down here. So log So log 2 of 16, again, it will be 4. But again, if I take a seal of it, again, it will be 4 only, right? So the problem is that this formula will not work if you have n which is in power of 2, right? So because it's giving me answer 4, but I know for 16 I need 5 bits because 16 is basically this, right? Right. So to handle this case as well, we can have a combined formula. So that formula is basically this. So B, oh my God. B is equal to, again, this is a floor function. This formula. Okay. So if you consider this formula, it will work in both the cases when n is not in power of 2 and n is in power of 2, right? So for example, if now n is 16, this will basically log of 216, which will be what, 4 plus 1 will be 5. It works in that case also, right? Is this clear? You can have, so there are lots and lots of material on this. This is something I use for preparing this particular slide. You can have a look at it or some other sources, right? It's totally fine. Is this okay? Okay, so let's go forward. Okay, now there is some, so now we are looking into hardware itself, right? So when you buy some computer system, right, it will tell you what is the clock speed, right? So a clock is something that is decides the speed of your hardware in some sense, right? So how is that the case? That is none of our concern at this point. What we want to understand here is like there is a clock and it has some purpose, right? How fast it is or how slow it is, that is none of our business at this moment. We'll just understand what exactly is a clock. So when you in your computer system, right, there is a chip or there is some module which has some kind of a crystal in it, right? And it generates a spike, basically a electrical spike, right? uh, at some fixed interval, right? So it's basically some crystal which oscillates, and whenever it oscillates, it's basically quartz crystal. Yeah, so quartz crystal or some, I don't know what they have in the latest systems. It basically oscillates at some very fixed period, and whenever it oscillates, it gives a signal in the sense like it gives plus 5 voltage output. So it's basically literally a hardware chip. It has a output wire. Again, when it literally has a wire. Okay, so it has some copper wire coming out of it, and after, let's say after 1 second it gives a pulse. It gives plus 5 volt after 1 second, and for 1 second it will give minus 5. This is for 1 second. Again, this is for 1 second. So for example, here for this particular time it will output plus 5 volts, which is again binary 1, right? And for this period, for this time, it will output basically minus 5 volt or 0 volt, whatever, right? Like depends on the system, which is basically 0. So it basically generates 1 0 1 0 1 0 1 0 at a very at fixed intervals, right? We don't care about what exactly that interval is, but it's at some fixed interval. And this is again, I'm enforcing this point again and again and again, because it's very important to understand what is hardware and what is software. Okay, this particular thing is actually present in your system. So there is a physical chip on your motherboard for this. Right now it's actually in the CPU, but doesn't matter, it's physically present. Is that understood? So we'll be needing clock everywhere. We will be needing clock while understanding CPU. We'll be needing clock while understanding scheduling. Okay, this is basically how we measure time, right? So it's basically a counter. We just count 1 2 3 4 5 6, right? So 1 2 3 4 5 6. So after 6 oscillations, do something. After 10 oscillations, do something. So this is what we use in case of scheduling. So it is important that you understand what exactly is a clock from operating system perspective. Correct. So yeah, so the chip oscillates. When I say chip oscillates, it basically there is some kind of a material inside. It just gives out this pulse at periodic intervals, right? How exactly it does that, we don't care. And when we say pulse, it is basically a voltage pulse, some electronic pulse. So positive is plus 5, negative is minus 5. Again, depends on the hardware. Currently, I guess it's 2.3 or something other voltages there. Point being that it basically gives you this 1010 signal, right? Irrespective of what voltages are. Okay. Yeah. Okay. So now we'll get into some of the kind of like important part of the computer. So this part that we are covering is basically computer organization from perspective of operating systems. Okay. So now we will get into what we call as memory. Again, there are multiple names for it. We call it RAM also. We'll understand why we call it random access memory. Sometimes in old literature it is called as core also, but in operating system generally it's called as memory or main memory. Okay. So to understand memory, we consider a C style array like this, right? So A is the name of the array, right? Then there are L elements in the array, and each element is of type byte, right? So 1 byte is equal to 8 bits. Okay. Again, this is something which has been already covered for you guys. I'm just using this so that we can connect it back to the memory in kind of like a logical manner. Okay. So this is an array. So it basically has size L. What this means is like it accepts the lowest index as 0. So there is an element called A of 0, and there is an element of A of L minus 1. Right. And ideally, there is no element at A of L. So anything after L minus 1 is basically illegal. So you might have seen that in C, if you do these kinds of access, you might get some memory error, right? Segmentation fault or something like that, right? In C, right? Okay, so just keep that in mind. If you violate this constraint, you get a segmentation fault in C, right? So we'll now convert this entire concept into hardware. Okay. So hardware in C, what you get is basically some array, and it is array from your perspective, right? In hardware, it's exactly implemented using this, what we can say. Okay, so it is exactly present, like your memory is exactly this. This is what is your memory. Your entire memory or RAM is basically this only. It is a very big array. It has a size L, and each element in this array is of type byte. That's all memory is. Okay, and it accepts this index 0 and 1, right? Only difference is that it is actually implemented in hardware. So if you do this kind of access, the hardware will say you are doing something wrong. Okay, so I'll elaborate this point in a bit more detail. Yeah. So for example, consider this image, right? For example, consider this image. This is exactly how your memory looks like. So these are elements in your array here. Each element is of 1 byte. So again, this is basically implemented with capacitors or something like flip-flops. I guess you have seen flip-flops somewhere or something like that, right? Or any other physical way of implementing this, right? So flip-flops are just one way. There are other ways also, more advanced ways. So each of this particular element in this array it consists of flip-flop, and ideally, since it's a byte, every element is 1 byte. It basically has 8 bits, which basically means it has eight flip-flops in that. Is this understood? Now this is physically present. Okay, it means there is a hardware for this. Is this understood? Okay, so now again, since we said this is an array, we will have some indices for that, right? So 0, 1, 2, 3 up to L minus 1, right? So this indices, if you look at this from the hardware's perspective, these are nothing but addresses. Again, I am saying physical addresses. Remember this. This will come in handy when we actually look into virtual memory, right? These indices are nothing but addresses, right? So 0 is an address, 1 is an address, 2 is an address. Literally from 0 to L minus 1, there are addresses, right? Now, since everything in the computer is binary, you just convert these indexes into binary numbers. Okay, so 0 will be 0, 0, 0, 0, 1, 1 will be 0, 0, 0, 1, 2 will be 0, 0, 1, 0, something like that, right? So we just convert this into the binary numbers, and that is what we call as address from hardware's perspective. So if you sorry, what memory means? Yeah, correct, right? So like I said, whenever I say memory in operating system, it's generally main memory or RAM. Okay, so these indexes are basically addresses, only that we represent them in binary numbers, right? So now how many locations are there in this memory? There are L locations, right? Because the size of the array is L, right? This is okay, right? Now my question is, how many bits will I require to represent this addresses, this entire addresses? So my lowest address is 0, my highest address is L minus 1. So how many bits will I require to represent total of L addresses? Again, I am saying whenever I say these numbers from operating system point, it's basically, these are basically unsigned integers, right? So this we already saw, right? Yeah. So C log L was one formula, but we came up with a better one formula, right? Which always works, right? Yeah. So it's basically floor of log of L plus 1. This formula works in both the cases, when L is in power of 2 or whether L is not a power of 2, right? So that will be the total number of physical lines present in this address. I'll elaborate that. Okay. So I have, this is my array 0 to L minus 1. From my perspective, I'm basically using unsigned integer to address this array. But for hardware perspective, this will be binary 0 to up to a into whatever L minus 1 has in binary, right? Whatever binary conversion is there, right? So this, what we call as addresses, require L, again this log L plus 1 bits. Let's call it B bits, right? To represent this number in binary, I will require these many bits, right? So to input to this array will be this many bits. This will be input to the array. Since my input will be again always in binary, and this will be my input, so I will pass to this array this B bits, and I'll get out. I'll get something as an output, right? So this B bits are basically what we call as address lines. Again, when I say now, whenever I say lines, it's basically some wire, physical wire. Okay. Literally, there is a connection from some other source to this particular memory, which is again physical, and there are B lines like that, right? Or address bus. Yeah, somebody said address bus. Even that is the correct way of saying it, right? So input to this physical memory is basically some address which are basically B line, B size bus. Again, B is in the B bits will be input to this particular physical memory. So there is again some chip known as memory controller. It will read this B bits and it will check which of these locations to pick, right? So you pass in some address and it will check which of these locations should be made active, right? So maybe this one and all not. So this is somewhat achieved using this multiplexer and demultiplexers. Right. Again, you must have seen this in this digital logic. You take it as B bits as input, and basically then you select one of this location using multiplexers and demultiplexers. Okay. Again, how exactly that is done, that is the part of your computer organization. But from operating system perspective, this is what we only need to understand. Again, I am emphasizing that this is basically passed on the physical line. So there is a wire, these B bits will flow on this wire, and then memory controller will decide in hardware. There is no code involved as such. In hardware, it will decide which one to enable, and it will make that particular location active. Okay. And when we say active, it's basically that whatever is there in this particular location, it will be connected to some other bus known as data. So it will be again 8-bit. Okay, so basically consider it to be like a gate. So operation is basically like this. You have multiple memory locations, and you only have one outlet, one output gate. So this is your data output. Right. This is your location 0, 1, 2, 3, and so on and so forth. And then you have address input. Okay. And this is your controller. It will basically read the address and connect either this one or this one or this one, right? Whichever matches this address, it will just connect this to your output bus. That's it. Right. Your address input will be read by this controller, and it will decide which of this location is matches this output, and it will just connect it to your data output. That's it. It is basically just a selector, right? So you have a gate and you select which one of these should be connected. That's all, right? And now once it is connected to this data lines or data output lines, right, there can be two operations that you can do. Either you can read it or either you can write it, right? So in your array also, you can either read from the array or you can write from the array, right? So now you have to tell this memory controller whether you are reading or whether you are writing, right? So there is an additional pin So again, when I say pin, it's basically a physical pin on which you can pass on some voltage, 0 or 1, or signal 0 or 1, right? So if this pin is 1, it means that you will be reading the data. If this pin is 0, it means you will be writing the data, right? So basically, to read the data from this particular any particular location from this memory, you have to pass in the B-sized address to this line, and then say that and pass a signal 1 onto this particular pin, and you will basically read it from the data line. Is this understood? Again, this is like very low level detail, but like this will be crucial when we actually go into virtual memory. So you pass in the address, you select the appropriate operation, it will get the data on the data line. For writing, again, you pass in the address here, you pass in the data here, and you say, I want to write. You set this pin to 0. Then memory controller will realize, okay, this is the active location. This is the data that I have to write it in here. Okay. Any doubt in physical memory? Okay. So let's go forward. Data is 8-bit at this point only, right? So I'm just explaining some very simple computer organization architecture. Our newer system might have different than 8-bit, might have 16-bit, it might have any other configurations, right? So, but as long as we are working in this operating system paradigm, we are considering that data is only 8-bit, right? So we will update that as we move along when we go to memory management and all that. At that point, we'll update all this understandings again. At this point, it just consider that it is to be 8-bit. That means it doesn't relation between address line. Correct. So address size of the address lines and size of the data lines has no connection whatsoever. So I can have 10 address lines and basically 8 data lines, or 16 address lines and 8 data lines, and 128 address lines and 8 data lines. It has no, what we say, it has no relation in between. Correct. I hope everybody understood that. Correct. So that is also an interesting question. So when we, so this can be answered in a way we do the C array. In a way we access the C array, right? So when you access any C array A, you pass in the address, right? I, some index I, right? This is what you decide. Programmer decides, right? Or I'll just say program decides. So it might be computed in an array, it might be computed through some other program, whatnot, but it's basically decided by the program what index to be used for accessing this particular array, right? Array does not tell you which index to use, right? Array will not tell you that this is the index that you should use. You have to tell array which index you want, right? It is basically the same thing. Since you will be the one who will be giving the address, this has to be unidirectional, right? You have to pass in the input. That's why it's unidirectional. But data is the other case. You can either choose to read or either you can choose to write. So that's why it's bidirectional, while address is unidirectional. Okay. So let's get to CPU now. Again, this is like a very high level picture of CPU. So I'll try to basically summarize this in few operations, and we'll go from there, right? So again, like basically what CPU does is basically addition, subtraction, is a multiplication, division. Then it can do this operations, right? This and or this basically logical operations and all that. It can again do bitwise operations like and or, again not and whatnot, right? So it can do all those operations. So you pass in two numbers, A and B. It again two binary numbers. It can add, all CPU operations are binary operations. So remember that whenever we are talking about hardware, everything is in binary. So it can add two binary numbers, it can subtract two binary numbers. It might be able to perform multiplication of two binary numbers, division of binary numbers. Again, this will be implemented as binary numbers only. This is again binary bitwise operations and all that, right? So all these things are implemented in hardware. So in digital logic, I guess the adder and subtractor might have been covered, right? Or it might be there in computer organization. Yeah, so it has basically some similar structure here also. All those things will be pushed into this particular block of CPU, arithmetic and logical unit. Right? How it is exactly doing it, we don't. It doesn't matter. We don't care. It is just that we can do all this operation that we should be aware of, right? Is this okay? Now the second part is basically this MMU. It's called memory management unit. So this is arithmetic and logical unit. So you have a name here also. This is basically memory management. Again, on a very broad level. Yeah. So don't go into that virtual and physical right now. Right. At this moment, we only know that this memory management unit will provide this address. That's all. You want to run some program, and it program needs some kind of an address, and this address will be generated by this MMU unit. Right. It does much more than that. But at this point, it basically generates whatever is input to this particular memory, physical memory, right? Physical memory requires address and this bit, right? And this data. So whatever is required by this required by this memory chip, again, this is a chip, will be generated by MMU. At this point, again, we will refine this as we move to memory management, virtual memory and all. Okay. Then there is something known as control. So its control is basically the part of the CPU which understands or tries to understand a program or code. So you write some code, right? So that CPU should understand that code. Now I'm using it in a very loose sense. There are other processes involved, like you have to compile the code, it have to convert it into assembly code, then it again have to convert it into byte code. Don't get into that right away, right? Don't get into that right away. Just understand what on high level what this control unit does. It basically tries to understand your code in the sense that it will read your code, it will break it down into some micro instructions, and it will then try to run that code. So you basically, when you say a plus b, again this will be in your bytecode or binary. The final code will be in binary. You will get to that. It will read this particular thing and it will try to understand, okay, these are the operations that I have to do, and that it will basically run those operations. That's it. Right. Again, I'm explaining this in a very high level manner. Once we get into a little bit of a compiler, I'll tell you what exactly this is. Even in process management, when we study this process fork and exec, right? At that point also, I'll elaborate this in a further detail. Okay. So any doubt in these three particular modules or subsystems? Okay, great. And finally, there are something known as registers. Again, these are basically flip-flops. Only thing is that they are inside your CPU itself. So they are on chip. They are on your basically CPU chips. And it basically means that CPU has a very faster access to this particular register. So again, when we look at the high picture, I will explain what do we mean by faster access. Right? It basically at this moment, just understand that this is also some kind of a special memory. Okay, it's just some kind of a special memory. I'll explain in detail in sometimes after 2-3 slides. Okay. Additionally, there are many things. So for example, there is something known as a cache. At this point, we don't care about cache. We'll get this cache. We'll again go to this cache when we actually get to memory management. So there is something known as translation look aside buffer. We'll again touch base on this at that point, right? Anyway, these caches will be covered in computer organization, L1, L2 caches and all that. It's just an optimization trick. For operating system, at this moment, we don't have to care about this, right? I just want to just give a hint that this is not the complete CPU at this moment. These are just some blocks of CPU which are of interest to us at this particular point. There are many other components inside it. Okay. Okay. So now this is what is something that we want to understand before moving forward. It's called Fetch-Decode-Execute cycle. So this is something what CPU does all the time. So whenever you start a system, all CPU can do is basically this. CPU knows this only. Again, this looks like straightforward, but this itself is a very complex operation. But ultimately, this is what any CPU does. It basically fetches something, it decodes it, and it tries to execute it. That's all. All right. So I'll explain that. So when we say fetch, right? So you have written some code. So maybe I write program code. Again, I'm assuming this code is something that this CPU can understand. It is stored somewhere in the memory, right? So your code is stored somewhere in the memory. So again, this memory is basically a big array, right? Again, 0, 1, L minus 1. This is a big array. And in somewhere in this big array, you have stored your code somewhere here, right? So it will, the CPU will fetch what your code from this particular location. So it will basically read this particular location. Now, when I say read, it will read from this memory. So it will, for reading this, it will require an address. Again, this read write bit, and again the data line. Again, this is data line, data bus. Okay, just to be clear, this is the address bus. So again, yeah, at this point, everything is physical. Everything is physical, right? So whenever I say CPU is fetching some instruction, or it's in the fetch phase, it basically sets the address to, it's basically sets some values to the address to the read write bit. Obviously it will be read only because you are reading the code, and then it will read over the data bus from this particular location. So now where to read from is decided by this particular register. So this particular register tells CPU that your next instruction will be coming from this particular address in the memory. From this particular address, you have to fetch it. And that register is called program counter of PC. Again, this is a very important thing. We'll touch base on this when we try to understand processes and context switches. This we will be needing in context switches. Okay, so okay, I'll explain it again. So what fetch does, right? So fetch basically has three. The main kind of like purpose of fetch is to read instruction from program code to CPU, right? So you have written your program, it is somewhere in the memory, it has to read from it. Now the first question, where to read from? So it is there somewhere in the memory, but where it is, that address you will need, right? What is the address? Again, now when I say address, it will be binary address, right? From what address should I read this particular instruction, right? So this address will be given in program counter. Again, who sets that address? I will get to that in some time. Assume that it's already there in program counter, and from this we have to read. So now we know from this address we have to read something, right? Now, how do we exactly read? We go back to our memory diagram. This diagram, right? So if you want to read something, what you have to do? You have to put that address onto this address bus, right? Again, you have to set this read write bit to read, and then you have to read it over this data bus, right? So this is what we already saw in the memory, and this is exactly what it will be doing. So to do this, put the address, again address basically is this thing, program counter, on address bus. Again, address bus is to memory. Then basically set the read write bit to read, and then read the data bus. Okay, so just a single fetch operations performs all these things. Okay, you have to put it on the address bus, then you have to set the bit properly, and then it will read it from it, right? Again, this happens very fast, right? So we don't even realize that this is happening, but this all happens in hardware. This is hardware. This entire thing happens in hardware. Is that understood? We have not at all touched software anywhere up to this point. Everything is going on inside hardware. Okay. So once this has been read from the memory, you said something in some code. You have written some code, right? It has now read it into its memory. So basically, second is decode. So the fetch reads instruction from memory. Again, the PC not change. Again, we'll get to that. Don't rush. PC will get to that again. Right. So now fetch reads the instructions from the memory. Now you have to understand this instruction, right? So for example, if you read instruction like add 1,2, maybe this is the instruction that you read from the memory, right? So now this means that you have to perform addition operation in your ALU with these as the parameters, right? You have to add 1 and 2, and you have to use some circuit in ALU, right? Again, I am saying circuit because all of this is hardware, right? So this decode logic or decode circuit will perform all those operations, right? Like it will set up all those operations. So it will understand that, okay, this is an add instruction which belongs to ALU. These are the parameters, right? And all that, right? It will basically understand all those things. And then once, and if you go into details of it, this is basically something known as micro instructions. Again, this is not of our interest from operating systems. You will get to know this anyway in your computer organization, right? So we will not dwell too much into it. But like if you want, if you are interested, you can look into it. So it will generate some kind of a micro program out of it. Even a single instruction, it will generate some micro program. Again, this entire thing is in hardware. All these things are happening in hardware. And whatever is the micro instructions that are generated by decode, it will basically execute. Execute in the sense that this guy decides which of the components or which of the circuits in CPU should be used, and execute will be actually run the circuits. That's it. So here it decides that ALU should be used, and here ALU actually runs. Okay. So everybody understood fetch, decode, execute? Any doubt in fetch, decode, execute? Again, this execute can be, need not to be ALU operation. It can be like store 10 into memory, right? Into memory. It can be that also. Okay. Okay. So I'll elaborate a bit. So whenever, so your CPU is basically a very dumb circuit, right? It is basically some, yeah, it's basically some circuit. It has basically different components, right? And your code has different instructions, right? So let me give you an example. These are again unrelated instructions. So first instruction that you have is basically this. Instruction 1 is basically this, that what you have to do is like add 1 and 2. This is your one instruction, right? Again, instruction 2 is basically store 10 into some address, let's say K. Okay, some address. This is something that is there in the program itself, right? So both of these instructions will be run by same CPU, right? Because there is only one CPU. This instruction will be run by same CPU. This instruction will be run by same CPU. The CPU has different components to perform these different operations. So for example, for addition, it will be using arithmetic and logical unit. For memory operation, it might be using MMU. Is that understood? Any doubt up to this point? No, right? So note that all these things are actually hardware, right? Hardware, when I say hardware, it's basically some circuit, right? It's a digital logic circuit, right? Some digital logic is going on. It's basically that circuit itself, right? So whenever it reads this instruction, it has to decide which circuit to use or which circuit to enable. So shall I enable ALU or shall I enable MMU, right? So in this case, you have to enable ALU. In this case, you have to enable MMU. Is this understood? Right. So this is on broad level, this is what we call as decoding. It is basically just decide which circuit to pick or decide which circuit to enable. And again, this is from operating systems perspective, right? Like this is a very naive way of saying what decoding is. It actually does a lot more of that. But from at this point, when we are just starting to learn operating system, this is enough for us, right? When you look into this computer organization, you will find out, okay, this is not what it is, right? There will be a lot of more things that are happening in decoding phase. But like, yeah, up to this point, this is okay for us, right? Once this decoding has happened and the circuit has been enabled, you have to run the circuit, right? So in the next phase, it will execute the circuit. That's it. Yeah. Is this okay? Right, let me check. Two values from memory when memory only be called, right? Yeah. So again, like that is a very complex program. We have to add two numbers and all, right? So in case we have to add two numbers on the memory will only be called. Yeah. So in that case, you have multiple instructions, right? Adding two numbers from the memory. Like I said, at this point, assume that this is a single instruction, right? Actually, this is not how the system works, right? This thing will be split down into multiple instructions again by your assembler or compiler. Compiler will break down this instruction into multiple sub instructions, right? So for example, load one into some register, then load two into some register, and then perform addition register one, register two, and then again save, something like that, right? At this point, what we are saying is that this is something that CPU understands. This is what we have assumed, right? This is not what CPU will understand in real life, but at this point, just for the sake of explanation, we assume that it understands it, right? So ideally, when we have program like this, let's say A is equal to 1, B is equal to 2, C is equal to A plus B, it will be converted into a very fine-grained program, right? So for example, move 1 to address of A, like whatever is the address, right? Then again move 2 to address of B, then again, and then again when we say C equal to A plus B, we have to first load what address of A to some register A, right? This is a register. Again load address of B to B, again this is a register, and then basically add A comma B. So it will add A comma B and puts the results into, again result is in A, and then basically save A to address of C. So something like, so this is the actual program that your compiler generates. Something like this. If you see, you have to tell everything, right? What should be put into one, what should be put into two, how should this addition be performed? So this single addition instruction actually has many small instruction, right? Load A into some register A, register B, then add these two registers, and then answer will be in register A, and then again you have to store into C, right? So these are the complex operations that compiler will do for you. So it will convert this into this particular code, and now this will be understood by CPU, right? So again, even this particular instruction decode, if this particular instruction is fetched by the CPU, this will basically have, this is basically assembly language. This is called as assembly language. Okay. So this, for example, this particular again will be involving MMU. This will be MMU, right? Again, this is MMU. This is MMU. This is ALU. So components which are involved in executing this instruction are different, right? So even in modern CPUs, there can be multiple also. These are not micro instructions. These are assembly instructions. These are not micro instructions. Okay, micro instructions will be present inside the decode logic only. Again, that's not what we are focusing on. The thing that we want to do is like this instruction will be there in Fetch-Decode-Execute. So for running this instruction, there will be a Fetch-Decode-Execute cycle. For running this instruction, again, there will be a Fetch-Decode-Execute cycle. That's it. How exactly decode operates, those details are not very interesting for operating system at this point, right? So just these details you will get into the compiler, this computer organization class, right? So again, that micro instruction and all is a little bit advanced. So you have to first go into this microprocessor and all, then only it will be much clear, right? But like, are the high level operations clear? So local memory, what I'll get into local memory, right? So when we see the entire picture, once I show the entire picture, it will be much clear. But up to this point, so clock, how exactly is clock used by this unit? We don't care. Maybe they use, maybe they don't. They generally do, but we don't care how exactly they are used. Again, that is the part of your computer organization. How exactly is this clock is consumed within these components? We don't care. It is used for this fetch, decode, execute in some way. How exactly it is used? We don't care. Okay. So any doubt in this high level explanations? Okay. So now let me show you the bigger picture. So this is what your computer is. This is basically known as the address and data bus. Yeah, this we can call it address plus data bus or just data bus. Anything. This is basically your motherboard, and nothing else. It has this copper lines and whatnot, right? It's basically that, right? So your CPU, your memory, and your other IO devices like keyboard and whatnot, right? Keyboard, mouse, and whatnot are connected to your motherboard, right? So whenever let's say CPU wants to read something, it will send the message to this memory controller through this address and data bus. So all these things will be there in this particular data lines only, address and data lines only. That's it, right? Now, if you see this is your main memory, and these are your registers, right here at this point. So if you see, if you want to read from the main memory, you first have to set up the address onto this. It will go through this line. It will reach your main memory controller. Then it will decide which of this particular locations to enable. Then it will enable that, and then again you have to read it from here again back to CPU, right? So if you see, the signal travels from CPU to memory and again memory to back to CPU. Is that understood? Again, everything is hardware. When I say signal, it's literally some current is going from this chip, CPU chip to the memory chip, right? So there is a pulse from here to here and again going back to here. So this adds what we call as latency. So traveling to send a signal and get the message back requires some time, right? So that is what we call as latency, right? So reading from memory takes some time, right? because it is in some sense it is physically very far away from the CPU, right? Is that understood? This is because of the physical distance between CPU and memory, right? There is some delay or there is some latency. These registers is a somewhat kind of like memory only, but they are directly on the same chip. So they are on the same chip. They are on the same chip as CPU itself. Okay. So it means that you can access them in a much faster manner because there is no latency. Or latency is very, very, very low because they are very physically very close to one another. Is this understood? So that's why registers are generally faster. Not generally, they are always faster, right? Compared to main memory because they are very close to one another. Only thing is that you cannot have. So for then one question can be asked, right? Like why can't I just take this complete block and directly put it into CPU, right? That is a valid question, right? Why even have this kind of arrangement, right? Yeah, exactly, right? So there is a cost issue. Cost in the sense like literally manufacturing such a design is very hard. There are some hardware issues with that and all that, right? Again, there are heating issues also. If you have too much hardware at the same concentrated into same area, it heats up and then there is a heating issue. Then you have to add a fan that basically increases the cost, right? So there are this physical and economical restrictions to such designs, right? So this is something which is economical and can be mass produced also. So this is something that we have followed, right? I hope this overall design, do you have any doubt in this overall design? Okay. So now when I say IO devices, right, this part we have not touched upon yet. So it is somewhat similar to memory only. Again, it will have some kind of a controller inside it. Again, it will have some pins, literally hardware pins, to which you can send some signal, for example, read and write signal, and you can read from these devices, right? So one such controller is basically USB controller, right? So USB controller literally has a USB chip. You can send, your CPU will send signal to this USB controller. It will then reply with some data or something like that, right? So operation wise, it is somewhat similar to memory only. In some sense, it's very similar to memory, right? So once we go to the file system, you will understand that at least in Linux, everything, all the IO devices are files only. But we'll get to that once we reach file system. Okay, it's quite interesting. Is this okay then? Okay, great. So let me know if you have any doubt up to this point. Okay, so now, yeah, this is what we will do. We have this, we understand that this is our computer. This is what you get when you buy a computer. This is what you get. And let's say there is no operating system, right? There is nothing in between. You directly have hardware, right? And you want to do this. You want to basically take two numbers and add them and put the value in this another variable C. Okay. That's all you want to do. So how to achieve that with this particular computer? Again, I am saying there is no operating system as such, right? So first thing that you have to do is you have to write this program. So this is your program, right? You have to write this program into the memory somewhere, right? So in your memory here, that program has to be written somewhere, right? So these are the steps that you have to do. You have to write this into your memory, right? Okay. Secondly, then you have to tell CPU that, okay, I have written my program at this particular location, somewhere inside here. You should start executing it, right? That you have to tell your CPU, right? Then how do we tell it? You basically set the program counter to that particular value, right? So because what happens is the program counter will, from the next time, it will start fetch, decode, execute from your program, right? Is that understood? Yeah, one part that I think I forgot to mention is that after every fetch decode execute cycle, program counter gets incremented by 1. So it basically reads your program sequentially. So after this, it will perform PC is equal to PC plus 1. I think I forgot that. So once the fetch decode execute is complete, it will increment the program counter by 1. So it will be reading instruction from the next address. So initially it read instruction from here, then it will read from here, then it will read from here, then it will read from here, and so on and so forth. It will keep on reading sequentially all of your program instructions, right? Yeah, so you have to set the program counter to a particular value, and from the next fetch decode execute cycle, it will start running your program, right? Then it will basically read this. It will read instruction one by one, this and this. It will execute it, and it will store the value into C. Whatever, right? Is this understood? That is how this particular CPU or this particular computer organization will execute this program. Is this understood? Okay. So now we'll go a little bit deeper into this. First question: which memory should I use? Okay. So I have this complete memory at my disposal, right? Now I have to write my program somewhere, right? I have to write my code somewhere, right? Where should I write? No, not secondary memory. I have this main memory, right? So my program will be written somewhere in the main memory. So I have these many addresses, right? 0 to L minus 1. From what address I should start writing? So it first is basically L is equal to, or maybe address 0. Somebody said address 0. This is your choice. Second one is like anywhere. Third one said depends on availability. Okay. So these are like, and many more, right? So let's understand each of this way, right? So this is definitely a good choice. I can start from the 0 address and start writing from it. But then what happens if like one of my program terminates? Again, I have to write another program. So for example, like I write one program here, it takes up to this particular, it takes up to this much memory, it terminates. Now I have to run another program. Then again, I will write from here. I will overwrite whatever was written here, correct? That also terminates, and again I have to go to the first program. Again, that I have to rewrite here again and again and again, right? So if you see here, if I'm just using the first initial address, I could have fit both of those programs into the memory because I have enough memory. But since I'm decided that, okay, I'll only write at the first memory address starting from 0, I'm not utilizing that memory completely. Okay, so again, there is another suggestion. We'll get to that also. But like, anybody understood issue with this? So basically, I cannot store multiple programs, right? Because every time I have to write a new program, I have to delete the old one, right? Fine. So one solution was that to store consecutively, we can store, right? So one solution for this was store consecutively. Store one after another. Okay, we'll get to that. We'll get to this solution. So now when somebody said anywhere, right? But again, anywhere in what? If some program has, if I use anywhere, I need to check some other program is not there, right? If I'm going to write something new, I should first ensure that there is not something already there, right? If So if I don't have any other option, I will unfortunately have to delete something. But if I have enough memory, and if still I am writing some overwriting some already written program, that is not good, right? Right? Is that understood? Yeah. Then third thing is basically depend on the availability, right? Okay. So this is somewhat similar to this, guys. Store one after another. So store one after another basically means that I have to keep track which memory is used by which program. Right, I have to keep track of that, right? So one after another is basically doing that the same thing. This is also doing again depends on availability, is also doing the same thing in some sense, right? Somebody says greedy approach. Again, if you say greedy approach, again you have to store the details, which part of the memory has been used by which program, right? So anyway, the point being that just to answer this simple question, you need some kind of bookkeeping about memory, right? Which part of the memory is used by which particular program, right? Is this understood? If I want to run multiple programs, I want to keep multiple programs into memory, I have to keep track of which program is where in my memory, right? Now this I have to do whenever I add a new program. Whenever I want to execute a new program, I have to do this, right? And that this is what operating system does for you. All these things that we are discussing right now, it's basically what operating system does for you. So don't get into details, right? Is this the solution or is there internal fragmentation or whatnot? Understand that there is a problem. Without an operating system, you have to do a lot of work just to run A is equal to 1, B is equal to, and C is equal to A plus B. Right? Don't worry about the solution as of now. Understand that there is a problem. That is the first part. Everybody agree that running a program on this on our own is very difficult because you have to do all those things, right? So if it would have been the case that I just want to run one program and I'm done with it, then no problem, right? That is a happy ending for everybody. But that's not what you buy a computer for. You never buy a computer for just doing A is equal to 1 and B is equal to 2 and C is equal to A plus B, right? Okay. So my question was this. So consider that this is the program that you want to execute on your system, right? If this and the first step of executing this program on your computer is basically to write this program somewhere into the memory, right? You have to write this program somewhere into the memory. Everybody understood that? Yeah. So my question was that I have this complete memory, which has L locations. Here, it has L locations 0 to L minus 1. Where should I write this program? That was the question. So I have location 0, location 1, location 2. I can start from location 0 and write the program from 0 to 10 or 0 to 20 or whatnot, depends on the program size, right? So that was one option. Start writing your program from 0th location. Is that understood? What was the question? Question was, where should I write this program into my main memory? And there were few suggestions. First suggestion was that always start with 0. That was the first suggestion. Second suggestion was that write anywhere you want, right? And third suggestion was depending on availability, and there were a few other suggestions, right? So one thing is that if this is the only program that I want to run in my entire life onto this system, then I am good to go, right? But is that why you buy a computer? Just to do some calculation and just throw it away later? No, right? You want to exactly, right? You want to do lots of video dekhna hai, gana bajana hai, and like what some creative activities or whatnot, right? So generally you don't buy a computer just to run a single program. You buy it to run multiple programs, right? हाँ, अगर इतना ही ऐसा होता तो लाइफ अच्छा था. खरीद के रन करके छोड़ दिया, right? It's not the case. Then the question is, if that is the case, it means you have many programs in your memory, right? That is something that is required from your side. As a user, you expect the system to do that for you, right? Now then this question becomes difficult, right? Ki, where should I store the memory? Again, the question is still the same. Ki, kahan store karna hai? Where should I store this new program? Right? So we saw that starting with address, always using the same address 0 is not a good way, because then you will be deleting some programs, right? Which you might need later also. That is one thing. Then when again if you store it anywhere into your memory, again the same issue is there. You might end up deleting something that you might need later, right? And then there are some suggestions depending on the availability. So you keep track of what memory is used by what program and what is the free memory, and you use the free memory. That was another suggestion, right? So is this understood? Somebody asked a question about explain the question, like elaborate the question again. Uh, is this clear now? Okay. So now you have to see, we have to start keeping track now, which memory used by which program, right? So again, like there are some suggestions like hashing and what, I guess hashing with block size and all that. Yeah, that are totally valid solutions, right? But that's not the point. Point is that whenever I'm starting a new program, I have to run all of this. Again, I have to write this code, right? I bought my computer for running addition and program something like that, but I still have to write all this code. कि bookkeeping कैसे करना है and all that, right? Imagine that anybody who is not from computer science or like any technological background, some other guy is like using this system. Would he be able to write this code? Yeah, exactly, right? जिसको मतलब बिल्कुल ही कंप्यूटर का कुछ पता नहीं है, he just wants it for some application purpose. Would he be able to write this code? No, right? That's why you need operating system. Operating system does this for you, so that you don't have to worry about it. So when we say operating system is designed for convenience, this is the convenience that we say. कि ये जो low level, these low level operations that are very crucial for running program in a safe manner, you don't have to do this. Operating system will do it for you. Is this understood? Okay. Yeah. So that's why handling hardware directly is very hard. Right. Similar thing goes for again here, right? We set it to program counter for P, right? So our whatever new process that we created, we set the program counter for P. Once this program ends, maybe I want to run another program, right? So let's say I have 10 other programs which I have already written into the memory. Once this program execution is complete, I have to run any of the other programs. Is this understood? So I want to initially I wanted to run the single program. Now I am saying that this program I want to run, but there are 10 other programs also, right? So what I want is like once this program terminates, once this execution completes, I want to run some other programs, right? Is this understood? Then the question is which other program? Which other program? Okay, again, we can discuss this in the same manner. These are the ways we can do it. The thing is that here, when we discuss this, we discuss this thing with respect to memory, and we got memory management in operating system. This was what we call memory management. We'll discuss this later in detail. And when we ask the same question regarding which program to run, this will be process management. Okay. So whatever resource you have, there is a management to that. So memory management concerns itself with main memory, process management concerns itself with CPU, and file system concerns itself with IO devices, right? So again, the same question, which and what, right? Which program should I run? What memory should I use? Which file I should use? All those things again fall under this management, and all those things the operating system will do for you, right? If you don't have an operating system, you have to write the code for all these things, and that will make using a computer a very bad experience, right? I don't want to write like kahan pe rakhna hai program every time I want to like play a song, right? That is horrible, right? Take the computer, right? So hopefully at least you guys know, have a little bit of motivation about why do we need operating system. Okay. So how to write a program without the operating system? You can do that. You can do it through hardware. You can literally connect a keyboard to your memory, and you can do it without operating system also. Exactly. Like at this point, that's not our concern, but you can do it through some hardware kits. There are specialized kits just for sake of demonstrating that this is the problem, and through that you can do it. Old system, you literally have to write into memory using that hardware keyboard itself, since you don't have any screen or whatnot, right? So you have to do it through some specialized hardware itself. Specific codes, yeah, correct. Okay, so this is like the final topic for today. Let me check my part. Okay, we can go. So yeah, so finally we get to interrupts, right? So when we say interrupt, it means we are interrupting somebody, right? So what we are interrupting here is basically my fetch, decode, execute cycle. So interrupt fetch, decode, execute cycle. So CPU is running something, he is doing something in very peace, chal raha hai kaam, and something happens and it basically has to leave that job aside and do something else. That's all what interrupts are. Okay. So for example, CPU is running some program B, it receives some interrupt. So it's basically an event. Okay, it is some event, right? It's something happens, right? We don't know, we don't care at this point what happens, something happens, and because something happens, it has to, CPU has to stop executing its current program and it has to execute something else, right? That's all what interrupts are. CPU was doing happily fetch, decode, execute, something bad happened or something good happened, whatever happened, it says, okay, I'll not do fetch, decode, execute, I'll do something else. Okay, that's it. Okay, so let's have a very simple example for this. So this is your CPU. Again, I am drawing the similar diagram. So this is your address and data bus or whatever, right? Any bus. And you had the IO controller here, right? Let's say this IO controller is for keyboard. Okay. And it is connected to this guy. And again, this is connected to this guy. Now you press a button, right? When you press a button or press a key, is basically equal to, there is some event. So what is the event? That you press a key? You pressed a key, right? That's it. So what should CPU do in this case? It should ask this question, which key was pressed? So CPU should check which key was pressed. Right. So whenever you press a button or press a key, CPU should check which key was pressed. Right. So to understand, to acquire this knowledge that which the key which was pressed, there is some code which checks the key that you press, right? There is some code. Who has written that code? We don't care. There is some code, right? Whenever you press a button, there is a code that CPU should run, and it will get to know, okay, I press V, or I press D, or I press O, or something like that, right? There's some code. So, so yeah, so you understand the setup, right? Okay. So whenever you press a key, there will be an electrical signal which goes through this bus and goes to CPU. So CPU is doing some Fetch-Decode-Execute. And in between, you just pressed a key, right? Then there is a signal saying that you pressed a key, goes to the CPU. CPU knows this signal is for keyboard, right? Because there is a number which goes with it. So there is a number. Whenever you press a key, there is a signal which goes from the controller to the CPU along with some number, right? So, and this is literally a physical signal. There is a pin on CPU which gets a signal 1 or 0, something like that, right? And it also knows that what is the number of this particular pin or particular signal, right? There is some number. And it knows that if the pin gets a signal with this particular number, it has to ask this particular question, or basically it has to run this particular code. Okay. So this is what we called as hardware interrupt. And these are the one like very straightforward to understand. Some event happens in real life, some event happens, and then there is a hardware signal to the CPU, what code to run. Okay. So now question is, how exactly CPU decides which code it should run, right? So for that, it has something known as a interrupt vector table. Okay. So it basically has some number in one. So it basically has 2 columns, something like this. On first column, it has the number 1 or 0, 1, 2, 3, so on and so forth. And here it has the address for the code that it should run. So for example, when I press a keyboard, there is an interrupt and number is, let's say, 10. So it will go, CPU will receive this interrupt and it will check this number 10. And then basically it goes here, check what is the entry for 10 in this particular table. It will find an address and it will run that code. Again, whatever address is there, it will set up this program counter to that and it will start running that code. So does CPU keep checking particular wire all the time? So no, right? So that is the whole point of having hardware interrupts. CPU doesn't have to check all the time whether there is a signal on a particular pin. Rather, whenever there is a signal, it will automatically like interrupt the CPU to run these things, right? Okay. So what you have just described is basically what is called as polling. So polling in the sense that CPU will keep on checking whether there is a signal or not, where there is a signal or not, where there is a signal or not, right? And this is basically wasteful, right? It's basically waste, right? Why do you always have to keep checking for an event that rarely occurs, right? So instead, other mechanism is that you develop your hardware such that whenever there is an event, it automatically transfers CPU to some code that you want it to run. That's it. And that's why hardware interrupts are for in the first place. They don't have polling, they have, it's basically called interrupt only, polling versus interrupts, right? Is this clear? Yeah. So whenever there is an interrupt, the CPU will get a number. It will take this number, it will check into this interrupt vector table. It's basically literally a table. It will match that number with the first column and it will check what is the address in the second column. Then it will load that address into program counter and again it will start executing. Right. Right. Is this okay? So it's similar to a function call. Only thing is that this happens in hardware only. So it's similar to a function call, but it's in hardware. So these are what we call as hardware interrupts, right? So there is another way of initiating an interrupt. which are called as software interrupts. Okay, so in hardware interrupts, the event is that the hardware has done something, right? There is the event is basically a physical event in hardware world, right? In the outside world. In software interrupt, the program itself has the signal. So program contains an instruction that calls an interrupt. Only when, and the instruction is basically INT, INT 10, INT 80, INT 20, whatever, right? If your program has this particular instruction, it will also trigger an interrupt, right? Again, it will do this interrupt vector table and what, right? But this is not due to some outside hardware thing. It is something that you have written in your program itself. That's why it's called software interrupt. The only way to change CPU job is to change program order. So hardware interrupt directly changes PC. It does not directly change the PC. It changes through this IVT table, right? It changes all those things through this IVT table. Again, that entire thing works because the entire thing happens in hardware. Interrupt servicing happens entirely in hardware. That's how it works. So we are discussing that this happens, this happens, this happens. There is no code for that. It is literally a circuit that does it all, which is frankly quite amazing, right? So that's why it works, right? If you have to write a program for that, it won't work. You have to have that hardware support for this. Yeah, correct. So this ISR is what we call as interrupt service routing. So when we say this code, it has to run for every interrupt, right? That code is called as interrupt service routing. So for a given interrupt, there is a code that has to be run, and that code is called as interrupt service routing. So again, routine is basically function in interrupt service function. What? Right. That's it. Is this okay? Yeah. So this is hardware interrupt is okay. Software interrupt is something that you call from your program itself. And why that is needed, that we will discuss in the next class. So from here, we will go to system calls now in the next class. This is just for understanding. So this is today's class was something basic things that you should know even before you start studying operating systems. So today's class was only for that. So IVT is something that you should know how it works in background, right? So for example, if there is some tricky question comes in the exam, right? Like which is somewhat related to this, how exactly IVT operates, right? So you should know that operating system uses IVT in some sense, right? You should not be completely relying on that. Okay, there is some interrupt and it will just take care of everything. How exactly that interrupt is served, that you should know. So for example, this interrupt vector table, right? So for implementing the system calls, operating system expands this table, expands IVT to add entries for system calls. Again, I did not discuss this today because we will discuss it tomorrow anyway, right? This IVT, I guess you will again, most of this will again be covered in CO class anyway. This is just some high level overview that you will be needing for operating systems specifically. Kind of, yes. So it's giving priority to whatever event that has happened. It need not to be a user operation. It is just some event, right? Need not be a user generated event. It can be system generated event also. For example, there can be a, again, like this we will study in process management. There can be a timer interrupt also, which is not user generated. There can be a timer interrupt also. But again, this is not user generated, right? This is something else that has system itself has triggered. So it is some event that has to be entertained at that particular moment. That's it. Is this okay? Side projects, at this time I don't recall anything. I'll let you know in tomorrow's class. So one good exercise is just to read the Linux code. So that you can do. Okay, any questions? Okay. We'll start from system calls tomorrow. I'll try to give some background before moving into that, but yeah. Okay.